If you don't already know the circle theorems, this will be quite tricky. So if that's the case, I'd recommend you check out my video on the circle theorems first. There'll be a link to that video in this video's description. So there are 6 circle theorems that you need to prove for your GCSE exams, and they look like this. We're going to go through each of these one at a time and look at its proof. We'll start with the one in the top left. The angle in a semicircle is 90 degrees. So in an exam question, it could be worded as follows. AB is the diameter of the circle, that tells us it's a semicircle, and it says prove that angle ACB is 90 degrees. Many of the circle theorems in this video can actually be proved in many different ways. I'm going to go through just one proof for each of the theorems in this video. So if you see a different proof elsewhere, it may also be valid. To start this proof, I'm going to draw a line from O to C. This line is a radius of the circle. So is the line from O to A and O to B. So all of those lines are actually the same length. We can indicate this on the diagram by drawing a line over each of those lines, like this. Every step that we mark onto the diagram we're also going to write down in words as part of our proof. So we've just shown that all 3 of those lines are the same length. So I'm going to write that OA equals OB equals OC, and I'm going to explain that. That's because they are all radii. Radii being the plural of radius. Next I'm going to mark on an angle and call it X. I'm going to go for this angle here, which is angle OAC. So we say let angle OAC equal X. What we're then going to do is go and find all of the other angles in these triangles in terms of X. The first one that's quite easy to spot is this angle up here. This is also equal to X because we have an isosceles triangle. So remember, everything we mark onto this diagram we're going to write down in words as well. So we need to explain that angle ACO is also equal to X and give a reason for that. That's because the base angles in an isosceles triangle are equal. Next we're going to look at this angle here, which is angle COA. Since we know the other 2 angles in that triangle are both X, we could subtract those from 180 and we'd find this angle. So angle COA must be 180 take away 2x. So let's mark this onto the diagram, and once again we're going to explain this step. The angles in a triangle add to make 180 degrees. Then we're going to find this angle here. So this is angle COB. This purple angle forms a straight line with the green angle, angle COA. So we know that those 2 angles must make 180 degrees. So to find angle COB, we start with 180 and then subtract the green angle, which was 180 take away 2x. It's really important that you include these brackets here. So now when we come to do the subtraction, it's 180. We need to do -1 multiplied by 180, so negative 180. But -1 multiplied by -2x, which is positive 2x. Now the 180s cancel and we're just left with 2x. So angle COB is equal to 2x. We need to give a reason for this step, which would be angles on a straight line add to 180 degrees. Now we need a bit more space, and we're going to find these 2 angles here, which I've marked in blue. So let's look at angle OBC first. Well, the triangle COB is also an isosceles triangle because we can see we have 2 radii once again. OC and OB are the same length. This means that the blue angles are also both equal. So if we subtract the angle we can already see, which is 2x from 180, we get 180 subtract 2x. This must be the sum of both of those blue angles. But since they're both equal, I could divide this by 2. So if I do 180 minus 2x divided by 2, I get 180 over 2, which is 90, and negative 2x over 2, which is negative 1x. So we find that angle OBC was 90 minus x, but that's the same as the angle OCB, which is also 90 minus x. So let's mark both of those onto the diagram. We need to give a reason for this step as well, and we've used this reason already. The base angles in an isosceles triangle are equal. Now we're almost ready to finish the proof. We were asked to show that angle ACB was 90 degrees. Well, if you look at angle ACB on the diagram, you can see it's made up of two angles. It's the red angle and the blue angle. So we could say that angle ACB is the red angle, which is x, at the blue angle, which is 90 minus x. Here the x's will cancel out, since x take away x is 0, so you're just left with 90. So we've now shown that angle ACB must be 90 degrees. Now let's have a look at our second proof. This time we're going to prove that the angle at the centre is twice the angle at the circumference. The question might say, prove that angle AOC is equal to 2 multiplied by angle ABC. We're going to start this question by drawing in a radius again, this time from O to B. We can see that all three of these are radii, so let's write that they're the same length. So OA equals OB equals OC because they're all radii. Next we're going to mark on two angles. We're going to call this angle here X and this angle here Y. So let's write that down. Let angle AOB equal X and also angle OCB equal Y. With these two marked onto the diagram, we can find many other angles in terms of X and Y. So firstly, this angle up here is also X because it's inside an isosceles triangle again. And in a similar way, this angle is also Y. So let's write those down but give a reason. So angle OBA must be equal to X and angle OBC must be equal to Y. And the reason is the base angles in an isosceles triangle are equal. Next we're going to find these two green angles here. They're angles BOA and BOC. To do these, we're going to look at each triangle separately. So if you look at triangle ABO, you can see that's an isosceles triangle and we've got two of the angles, they're both X. So to find the missing angle, we do 180, take away those two angles, so 180 take away 2x. It's a similar story for the other triangle, but it'll be 180 take away 2y. So we need to give a reason for this, which is angles in a triangle add to 180 degrees, and we'll mark both of these onto the diagram. Then we're going to find this blue angle here. Here we have three angles that are around a point. Angles around a point must make 360 degrees. So to find the angle AOC, we could do 360 subtract the other two angles, which are 180 minus 2x and 180 minus 2y. Again, we need these brackets here. When we work this out, we have 360. Negative 1 times 180 is negative 180. Negative 1 times negative 2x is positive 2x. Negative 1 times 180 is negative 180. And negative 1 times negative 2y is positive 2y. Here, the 360 take away 180 take away 180 is 0. So we're just left with 2x plus 2y. Now we need to remember to give a reason for this step, and it was angles around a point add to 360 degrees. Now we're almost ready to finish the proof. If you look at 2x plus 2y, we can factorize out a 2. So it's 2 lots of x plus y. Now if we remember in this question, we were trying to prove that angle AOC is 2 lots of angle ABC. We've written down an expression for angle AOC, it's 2 lots of x plus y. And if you look closely at angle ABC, it is equal to x plus y, because to get it, you'd add those two angles together. So we can replace this x plus y with angle ABC. So this is equal to 2 lots of angle ABC. And we finish the proof. Now on to proof number 3. This time we're going to prove the opposite angles in a cyclic quadrilateral add to make 180 degrees. The question might be worded like this. Prove that angle CDA plus angle ABC equals 180. We're going to start this one by marking on those two angles. We'll call the angle CDA X and the angle ABC Y. So let's write that down. Let angle CDA equal X and angle ABC equal Y. Then we're going to draw in a radius from O to A and O to C, like this. Next we're going to use the theorem that we just proved. The angle at the centre is twice the angle at the circumference. So we can mark on this angle here as 2x because it must be twice angle CDA. So let's write that down. So angle COA equals 2x. And for exactly the same reason, this angle here will be 2y, since it's double angle ABC. So let's write that down. Angle COA equals 2y. Now this is somewhat confusing because we just called both of those angles COA, and they do both start at C, go to O, and then finish at A. To distinguish between which angle we're talking about, we could call one of them a minor angle and one of them a major angle, the minor one being smaller and the major one being larger. And don't forget, we need to give a reason for each step, so we could say for this one, the angle at the centre is twice the angle at the circumference. Now because both of the angles we just found are around a point, they must add to make 360. So we could write that 2x plus 2y equals 360. And we need to explain that as well. Angles around a point add to 360 degrees. Now if we take this equation here and divide both sides by 2, on the left hand side, 2x plus 2y divided by 2 is 1x plus 1y, and 360 divided by 2 on the right is 180. So we find that x plus y equals 180. But x and y were the original angles that we labelled, angle CDA and angle ABC. So if x plus y equals 180, angle CDA, which is x, plus angle ABC, which is y, must equal 180, which is exactly what we were trying to prove. Now we move on to the fourth proof, so we're going to prove the theorem which says the angles in the same segment at the circumference are equal. So this one could be worded as follows: prove that angle ABD equals angle ACD. To do this, we're going to mark on two radii from O to A and O to D. And then we're going to label the angle AOD as x. So let's write that down. Angle AOD is equal to x. Then we're going to look at this angle here, angle ABD. This angle's at the circumference, so it must be half of the angle at the centre. But we labelled the angle at the centre as x. So this angle must be half of that, which is x over 2, or half x. So angle ABD equals x over 2. And we can give a reason for this, because the angle at the centre is twice the angle at the circumference. Then we're going to look at this angle here, angle ACD. And this is also the angle at the circumference, so it must be half the angle at the centre. The angle at the centre was x, so this is x over 2. And it's for exactly the same reason, the angle at the centre is twice the angle at the circumference. Now this is all we actually need to do to complete this proof. Angle ABD is equal to x over 2, but angle ACD is also x over 2, so they must be equal. So we can simply write down that angle ABD is equal to angle ACD because they're both equal to x over 2. For the next theorem, we're going to look at the alternate segment theorem. So this one could be worded as prove that angle ACT equals angle ABC. Once again, we're going to add some radii to this diagram, one from O to A and one from O to C. And then we're going to mark on the angle they've given us in the question, angle ACT, and we'll call that one X. So let's write down angle ACT equals X. Now if you look at the angle OCT, this is where a radius meets a tangent, and a radius meets a tangent at 90 degrees. So this angle here is a right angle, which means we can find this angle that I've marked in blue by subtracting the angle X away from 90. So the blue angle must be 90 minus X. So let's write that down, angle ACO equals 90 minus X. Now because the two red lines are radii, they're equal in length, which means the triangle AOC is an isosceles triangle, which means this angle here is also the same as the blue angle, 90 minus X. So let's write this down as well, angle CAO is also 90 minus X, and the reason is base angles in an isosceles triangle are equal. Then we can find this angle here, since we know the other two angles in that triangle. So if we subtract those away from 180, we find that angle AOC is equal to 180, subtract 90 minus X, and subtract another 90 minus X. This is 180, subtract 90, but we do negative 1 multiplied by negative X, which is positive X, subtract 90, and then plus X again. 180 take 90 is 0, so we just have X plus X, which is 2X. So we can mark this onto the diagram and give a reason. The angles in a triangle add up to 180 degrees. Next we're going to look at this red angle here, angle ABC. This is the angle at the circumference, which must be half the angle at the centre. The angle at the centre is angle AOC, which is 2x, and half of 2x is 1x. So angle ABC is just equal to x. So let's put that on the diagram and give a reason. The angle at the centre is twice the angle at the circumference. Now we're almost ready to finish the proof. We were trying to prove angle ACT is equal to angle ABC. Now angle ACT is x and angle ABC is also x. So we can write down that angle ACT is equal to angle ABC because they're both equal to x. And that's the proof complete. And now on to the final proof. This time we're going to prove that the radius bisects a chord at 90 degrees. Now I'm going to be completely honest with you here, if you do AQA maths, you don't need to know this proof. It isn't mentioned in the teaching guidance when it lists the proofs you need to know. So if you do AQA for maths, you're welcome to leave this video now. But if you do, please drop me a like or a comment because I don't think most other creators would give you this information. If you do Edexcel though, stick around because you do need to know this, it's mentioned explicitly. So the proof might say, OB is perpendicular to AC. And then it says prove that AP equals PC. We're going to start this proof like we have many proofs so far by drawing on some radii. We're going to connect up from O to A and O to C. And since they're radii, they're both equal in length. So let's write that down, OA equals OC, because they're both radii. Now we're told in this question that OB is perpendicular to AC, which means they cross at 90 degrees. So we can mark on some right angles here and state that angle APO is the same as angle CPO because they're both 90 degrees. Next we're going to observe the fact that this side here OP is common to both of the triangles, APO and CPO. So let's write that down. OP is a common side to both triangles APO and CPO. Now this is enough information to show that these two triangles must be congruent. using RHS, which stands for right angle, hypotenuse, and side. They both have a right angle, their hypotenuses are both the same since they're the radii, and they have another side the same, which is OP. So we could say that triangles APO and CPO are congruent due to RHS. Since the two triangles are congruent, their sides must be equal in length. So we could write down, since they're congruent, we have, and then if we start by looking at the radii, OA and OC, we know they're equal in length, which is the hypotenuse. And this might seem a bit silly to write down, but they both have the side OP, so OP equals OP, that was the common side, which means the remaining sides that we haven't looked at must be equal in length. The remaining sides on those triangles are AP and PC. So we could write down, therefore the remaining sides must also be equal in length, so AP equals PC, which is what we were trying to prove.